So we have DC tax and AC tax. And they're basically generators, but they're unregulated. So both of them work off permanent magnets. So with permanent magnets, we can't change the strength of the field, right? So if we don't change the strength of the field and we don't change the number of coils of wire, then what depends on how much voltage a generator will put out. Has nothing to do with the resistance. The resistance of the coil, a lot of people will say the amount of voltage a generator puts out determines on the gauge of the wire, and that is totally false. The gauge of the wire determines the resistance of the generator, and what does R do? It drops a voltage if you put current through it. Okay, so the gauge wire they use inside an alternator does not determine the voltage the alternator pods put out. It determines how much current you can get out of the alternator. Okay, y'all understand the difference? So when we talk about the amount of voltage, current never came into play. What determines the amount of voltage if we put it into an unloaded source, or we don't try to load the generator? What determines how much voltage we get out? What three things determines how much voltage we get out? The speed, right? The speed of the motion, or the speed, in this situation, it will be the speed of the generator. What else? Three things that determines how much voltage we get. The strength of the magnetic field, right? And then what else? The number of conductor loops. Okay, so inside a generator, what two things don't we? Inside these, if it's a permanent magnet, we don't control the strength of the field. And I don't take this thing out and rewind the armature, right? You understand? So I don't control that. So what controls the amount of voltage we get out of a tach generator? The speed of the motion, right? Y'all understand that? So that means the faster it goes, the more voltage it puts out, and the slower it goes, the less voltage it puts out. And of course and it's linear too. So these guys are very, very popular because they're really linear. The only little problem we have is that currently we're living in a digital world and these are analog devices. Okay, y'all understand that? But that's no big deal. Even on PLCs, we can get what they call analog to digital converters, right? So we can definitely do it. So everybody okay there? That sounds like a really good test question. Probably not on this test because this test we're not doing speed, but it will be on the next test. And these are the way these work, right? That they put out more voltage. Now AC generators, tach generators, not only put out more voltage, but their frequency changes. Okay. So we can easily turn a AC generator into a digital signal just by not rectifying the AC and just clipping it off. I'll show you. Very, very easy to do. All it takes is a diode. Normally we would run it through a transistor to get a really good digital signal. But this is the little MG set that I made. So what we're doing is just we have this hooked up to an MG set is when you take a generator and hook it to a motor, right? So what we're doing is we're just simulating what would actually be out there, because these are little bitty things. Now your DC motor, of course, doesn't have to be permanent magnet. The advantage of a permanent magnet DC motor, of course, it's extremely cheap, but the disadvantage, of course, is that you get almost no horsepower added at all. So let's see, how do I zoom these? I don't see a zoom, do y'all? Something's going on with this camera. I can't figure out how to make it full screen. No, it doesn't work. It's a good point, see, but no edge dragging. All we got is controls. Here we go. So we can zoom out here, but this is the best we can do. But there's no full screen that I see. Huh? Yeah, preferences it doesn't have anything either. And then updates, that's the only thing we have available. So here's the MG set right here. Okay. And you can see we just got a coupler that couples. Now, in a little while, we're going to use the encoder wheel over here that we looked at the other day. We could use either one of these for the motor. So, and then so what we'll do is we'll use this one for the tach generator. And let me get my power supply here. I think I left my jumpers on here before we can take them off. Now the polarity or the direction of rotation determines on the polarity that we put on the rotating part, which on the DC motor we call it the armature. You'll see some people call it the stator, but technically that's the name we use for the rotor. Technically that's the name for the rotating part of an AC motor. But you see some people get that wrong, and it's no big deal. In fact, the rotor even makes it more clearer what part we're talking about. But as soon as I turn this on, I don't know, this is good over here. You can actually see this over here start rotating, right? And of course you can hear it. Okay. Later on we'll figure out the speed. Some of y'all that was in the class last night will be able to hopefully figure that out once we hook up our encoder out here. So what I'm going to do is I'm going to take my voltmeter, if we can get them up here at the same time. And I've got it on DC volts. And then we'll just look at the output of the generator. I don't know if I've got any more alligator clips or not. I need to make sure I bring them. Now this direction would determine the voltage. Huh? Okay. Looks like my meters. Oh, okay. This meter. So here we go. This is what we're getting out. Can y'all see that? And of course. Now, what we'd have to do here, of course, how would I know the speed? Huh? So notice when I slow my motor down, the output of my generator does what? Goes down. So if this is 12 volts, and if I dropped it down to 6, what do I know? It's half of whatever speed that was. But we can't do the transfer function right now unless we know the maximum speed of the motor, right? So what we'd have to do is know the maximum speed of the motor. If I knew the maximum speed of the motor, right, you understand, and I knew the maximum output, then we could calculate the transfer function and get volts per RPM. Okay. But I have to know the speed of the watt of the motor. So we'd have to put a tach gauge on this or something and see if that's what it is. But this is what I want to show you. So this guy here, so this is pretty neat because it's almost exactly 12 volts when I have it running full speed. And So whatever that speed is, if I drop it down to 6, that would be half speed, right? You understand? If I dropped it down to 2, then that would be 1/6 of the speed. Right? So what we have now is we have a really good representation of taking a RPM and converting it into an electrical unit that we could do what? That we could measure, right? And this is a DC tach. These guys have been used for years in closed loop systems to determine the speed of a motor, because some processes have to be done at a precise speed, right? Now, we had a lot of speed control on number 4 galvanizing line because they had to run it through a furnace, and the furnace was, good gracious, probably 100 yards long. And what they were doing is they were getting it ready or up to a certain temperature so it would accept the zinc. So it had to be at a certain temperature, right? So what did that mean? Well, they mean they had to have the furnace at a temperature, and they had to run that strip through that furnace at a precise speed. And then when they dipped it down into the zinc to get the exact coating they needed on that thing, they had to run it through that zinc tank at a precise speed, right? Because the slower you ran it, the thicker it would go on there, and the faster you ran it, the thinner you went on there. So the speed that they ran it through the zinc tank would determine the thickness of the zinc coating that they put on the galvanized steel. So a speed control on that line was very precise, very precise. Even run it through the chemical bath to clean it and get all the goopage stuff off. You know, it's a lot of acid and stuff like that. If they ran it through slow, then the acid would react too much, right? And do too much damage. If they ran it through fast, then it wouldn't clean it like it was supposed to before they dipped it down in that zinc. So speed control sometimes have to be very, very precise, or the process that it's doing is not going to be that, right? Everybody understand that? So speed control. Now, what's nice about this unit, like I said, this guy used to be the speed control on a floppy drive. And so this is a combination of both a DC motor and an AC tach, and that's why it's got 4 wires coming out of it. And it's a permanent magnet, so that means we don't have to control the field. So most of your DC motors, and if you're troubleshooting, of course, we're going to have to go over those. And we went over those in motor controls too. Your DC motors that we have the best control over, we can not only control the armature voltage, we can also control the field voltage, right? So if I increase the field voltage, the motor gets more torque, but it slows down. If we decrease the field voltage, we get less torque, but the motor speeds up, which is kind of strange, unless you understand the motor. If you increase the armature voltage, it speeds up, and if you decrease it, it slows down, right? You understand that? So using both the field and the armature, they could not only control the field, the speed, but they could also control the torque of a DC motor. So you get a lot more control of what you can do with a DC motor over an AC motor. So this has got an AC generator in it, but we can't control the field, and it's spinning so the way we control the speed of this guy is we just increase the armature voltage, right? I think the blue and the red, hopefully, we'll look at this in a minute. I think that's the actual motor. And then the yellow and the green wires, I'm pretty sure that's the tach generator. Now the voltage you apply to the armature determines the direction that the motor rotates, right? Now this has got a piece of tape on it. Of course, so I can control the speed very precisely with nothing but voltage, right? Now, of course, what we can do with this is we can use a meter again, but I'm gonna have to put my meter on AC, and I'm gonna have to get some more wires. People. It's tripping. So put my motor up, put my meter on AC instead of DC. And then we'll look at this one in the oscilloscope too. So we'll see what this puts out. I think this one right here, I think it's a 12 volt. In fact, I know it's a 12 volt motor. We don't need to go over 12 volts on it. So it's about 10 volts. So if we dropped it down to about 5, we know it's running at half speed, right? Okay. But this is AC. So what I'm going to do is fire up my oscilloscope. And I don't know if I've got the stuff I need in here to convert it to digital. But we can very easily take AC and convert it to digital. So what advantage does a motor, I'm sorting my leads out, what advantage does an oscilloscope have over a meter? Yeah, it's not pretty much. You can see what's there. Voltage relative to time. So here's the oscilloscope. And it develops a waveform just like Alabama Power does called sine wave. If you had AC, you know what that is, but if you hadn't. So AC is generated on a circle. How many degrees in a circle? 360. And then if we drop a vertical down from any point along this line, we create a right angle. Once we create a right angle, then we can use trigonometry to calculate sides. Well, if we move through 360 degrees, so this would be 360 degrees, if I drop the vertical down anywhere along this line and took the sine of that, then it would, of the angle, it would give me what we call the instantaneous voltage. So the instantaneous voltage varies with the sine of the angle. So if I knew the peak voltage, I can multiply the sine of any angle, and then it would give me the instantaneous voltage. So this is called a what? It's called a sine wave. That's how it got the name, because it varies with the sine of the angle, multiplied by what we call Vt. Now let's change the speed here and see what happens. So notice I'm lowering it down. So the time's getting longer, so the frequency's going down, right? So if but also notice what the amplitude went down. So the amplitude's going down. You can actually see it stuttering a little bit when it hits that tape. Okay. And here the frequency's going up and time's going down. But also what's going up? Yeah, the amplitude. So we can use two things here to get the speed. We can use the amplitude of the AC. In fact, if I needed to take it into a DC circuit, we can rectify this. It's not real hard to do. So we have what we call rectifier circuits. We which takes AC and converts it to DC. Which is every car that we drive now has that in there, right? So we have alternators, but we have a DC system. So they have a solid state circuit in there we call a rectifier circuit that's taking what? AC and converting it into DC. Also, we can take that and run it to a digital circuit and flip it up, and turn it into digital. So we could use an AC tach generator as into a digital circuit and use counters, or we could run it into a DC circuit by taking this and rectifying it. So this is an AC tach generator. Now AC tach generators, what advantages do they have besides giving us two means of measuring speed? So what does a DC tach generator have on it? It's got to have commutators and it's got to have brushes, right? You understand that? To take the AC that's normally being produced by the rotor and convert it into DC. So a DC generator's got a commutator and a brush. AC tachometers don't. So AC tachometers have a lot less maintenance on them than DC tachs do. They last a lot longer, right? You understand? And if I needed DC, I would just put a rectifier circuit on this and turn it into DC for my control circuit. So pretty neat, but if I took this and converted it to digital by using a transistor, what we call a saturated switch, we can take this very easily and convert it into digital, and I could take it directly into a PLC, to a high-speed counter, and count it and do the math. So now I can figure out the RPM of the motor because now we have a frequency. The frequencies are rated in time. So we'll spread it out and get one cycle. So it's like last night. I have it on 500 microseconds per minute. What's that? No, we're starting right here. So that would be 1 millisecond, right? That would be 2 milliseconds, 3 milliseconds, 4.5 milliseconds. So that's for one, what we call cycle. Now this is in seconds, and my speed's in long. Now what's nice about this, so what we're going to do is, this is AC, so this is not an encoder. So what we're doing is we're getting one cycle per revolution. Yeah, well, if it's one cycle per revolution. What we don't know about this is if we come over here and we have two sets of magnets, then we would get 2 cycles per revolution. So the more slots we have in our commutator, so we can count the number of slots in our commutator, and that would tell us how many cycles we get per revolution. So let's say we have 2 sets. Okay, so that means we'll get 2 cycles per revolution. Like I said, we got to figure this out.
So you can, like on it, you encoder, you use pedals, you use
The number of slots on the. Here what we would use is the number of slots on the encoder. So if we got 4, then that means it takes 2 of them to get a north-south field, right? Understand that? And that's what we would get out of this. We get 2 cycles per revolution. If it's got 6 of them, then we would get 3, right? Which would be very unusual for a motor this size. So this is probably got 2. So that means we get 2 cycles per revolution. So the first first thing I would do is take this and multiply it by what? 2. And that would give me what? 9 milliseconds. Okay, what would I do next? Take the reciprocal of this, right? 1/9 milliseconds. And that would give me revolutions per second. That would be what? What did it say? That's milliseconds there. Should be writing this down on PowerPoint, right? So if y'all were listening to this, instead of just listening to it, you can see it. So two cycles per revolution is probably right for this motor, and we can't get into it to see it. So again, what we would, to really know this, we would have to put a tach gauge on this thing, and we would have to measure the RPM. And I think we got a tach gauge back there, but an optical tach gauge. But last time I played around with it, I don't think it was working. So we'll use two cycles per revolution. So we measured our time with our oscilloscope. We came up and got what? Yeah, so we got 4.5 milliseconds. And then we multiplied it by the number of cycles. So we got 2. So this gave us 9 milliseconds per revolution, right? Then to take time and convert it into frequency, which RPM is. It's so many revolutions per minute, right? So I'll take this and convert it into frequency. So F would be equal to 1/9 milli, which would be what? 6.67 revolutions per second, or RPS. And so to get it into RPE, what's that? What? Oh, I'm sorry. Yeah, thank you. I just did that to pay attention. Well, no, not necessarily. You can do it in different orders. What's nice about multiplication and division, you can do it in different order and come up. So what do we get when we took the reciprocal of this? This would be revolutions per second. So revolutions per, this is revolutions per second, is 9 milliseconds, right? I don't know. That's not true either. Y'all getting me confused. So to turn it into revolutions per second, what do we need to do? We need to take the reciprocal of this. So I'm taking 1/9 milliseconds. And what does that give me? What's that? So 11 milliseconds. 11. What's that? 0.11? 111. Okay. 111. Oh. And then this would be revolutions per second, right? And then we would. What's that? So this is. So we took you took the reciprocal of 9 milli, not 9 milli. Okay, so it's like I was thinking, say this is not going to come up to be milli. So something's going on. Okay. Okay. Yeah, but we wouldn't go that fast, I don't think. What's that? Now you can't take 111.1 and not come up and get thousands, right? Yeah, so that motor's not running that fast. So what would that probably mean? Yeah, it's not running 2 cycles per second. It must be running at what? Yeah, 1 cycle. Yeah, that motor wasn't running at 6,000 RPM. Not saying it couldn't do it. DC, one advantage, what sets the speed, what's the primary thing that sets the speed of an AC motor? Yeah, the frequency. When we spin the field around the outside, we're inducing a voltage into the rotor. So we call them induction motors. Okay. So when this thing rotates, it's going to try to lock into that. It's never going to do it, because if you do, you wouldn't get any motion to induce a voltage. So all induction motors have something we call slip, which means the rotor always runs slightly slower than the field speed. So the speed of an AC motor is equal to 120 times the frequency divided by the number of magnetic poles. And then minus the slip. So that's the actual speed of an induction motor. So if you know the percent of slip that the motor had, then you can literally count the speed. Okay. So we got 2 things we need to do. So it looks like I can't change. I can't change 120, because by the way, this is the frequency. Alabama Power runs at 60 cycles. So the actual formula is RPM times 60 times the frequency divided by the number of pole pairs. But a lot of people, so that means if I got a north and south, that would be 1 pole pair. But we don't say 1 pole pair motor. We say a 2 pole motor. So that's why they changed that's why they just double that and say the number of poles, right? So it's basically the same same thing. So what we can do is we can change the frequency. So we have what we call variable frequency drives, which is basically a misnomenclature for what we have to do with an AC motor. The problem with an AC motor is that its opposition varies with frequency. We call it X of L is equal to 2 pi FL. So what happens if I raise the frequency? The opposition of the motor is going to go up, which means the motor is going to pull less current, and the motor is going to create less torque, and we can literally stall the motor. So AC motors, we can't control the speed of an AC motor with nothing but frequency. So what we have to do is we have to increase the voltage. So a variable speed AC motor, if we raise the frequency, we raise the voltage. If we lower the frequency, we lower the voltage, right? You understand that? So they're basically variable speed drives is what they are. So AC speed drives have to control 2 things. They have to control what? Voltage and motor. So we're not using the voltage to change the speed. We're using the voltage to keep the torque of the motor constant. Because if I raise nothing but the frequency, the motor would lose torque. If I lowered the frequency, the motor would pull more current and try to create more torque, right? And we don't want a 3 horsepower motor. We want it to create what? 3 horsepower, right? You understand? So we don't want the torque of the motor to vary with the speed of the motor. We want the torque of the motor to stay fairly constant when it's operating. So we calculate what we call a voltage to frequency. It's real easy. You look at the motor and you see what the voltage the motor is rated at, what frequency it's rated at. You take the voltage divided by the frequency, and that would tell, if you maintain that voltage per hertz ratio, then you can control that speed of that AC motor over a wide range. DC motors, all we have to do is just change the voltage to the armature. And if I increase the voltage, what does it do? Yeah. And by George, DC motors, you can make them suckers scream until they sling themselves apart. So they will literally sling, or the friction of the motor, the motor can't turn the friction. It can't turn the friction inside the motor, the air friction with the big rotor moving inside there, because it's got teeth and wires and stuff on it, and also the friction of the bearings and everything. So we can sling an AC motor. We can sling a DC motor apart. Because what sets the speed? Yeah, so you can see, I think. So we're running it faster than what it's supposed to run. So you don't need to run the motor above its rated voltage, because that's where they guarantee that it won't do what. You got to come forward, because all those windings. So let's redo that. So that's a little. So DC motors still have the advantage of being easier to control. What advantage does AC have? Motors have? Yeah. So the overall, and the motors are cheaper per horsepower, so they don't have as much copper wire in them, because they get their opposition from X of L. DC motors gets their opposition from the R of the wire. So if you ever looked at the coils of the field coils of a DC motor, there's going to be a bunch of copper in that. It's going to be real thin. You look at an AC motor, those coils are going to be pretty big, because they get their opposition from what? From X of L. Yeah. So AC motors are cheaper. You don't have to have brushes on them. You don't have to have commentators on them. So AC motors are a lot cheaper per horsepower. So that's why they're dominating the variable speed now, because of the price, not because of the ease of control. So let's do it at 1 cycle per. Let's do that. And some way we can do it in our head. So what do we come up and get? 6,000 something? Well, we just half that. So this guy was running about what? 3,000, which is pretty good for this motor. That would be probably about right, because we were running it up in here, right? And you can see the tape spreading out just from the centrifugal force. So this is the actual motor that came out of the floppy drive for a 5-inch core, 5.25-inch floppy drive, and this was the motor that they used for speed regulation. So they used that AC tach generator back into the electronics to keep the speed at 300 revolutions per minute. So they ran the motor pretty dang slow, because the floppy disks were made out of a flexible mylar plastic, and you couldn't spin that stuff real fast, because if you did. And it was inside a jacket that had a slip sleeve in there, but still the platter, the little disc in there, was in contact with the side. So if you tried to spin it too fast, you'd create too much heat, right? You understand that? And then of course, then it was made out of flexible plastic, and you would sling that stuff apart. Pretty neat. So that's why your hard drives have metal platters in them. They don't have plastic platters. So that's the two tach generators that we were looking at. And what's neat about this is this guy here could actually be used as an encoder, right? Because what does it change? Its frequency changes with voltage. All I'll have to do is just take that and convert it over to digital. So I won't even hook up the encoder. So I did remember to bring these over, guys, this time. Anything else I told you I was going to bring over? Dunkin' Donuts? Yeah, I wouldn't. So the first lab that we're going to work on, it's not here. All of So these labs are made up exactly like the lab motor controls work. So we have a chapter, and then the chapter is divided back into pairs, right? So we have a big discussion at the start of each chapter. So y'all can keep that. And what I've done is I've ran this off separate. That's part of the labs. The first lab we're going to do is Oh, yeah, that one's rough. I got that. I understand. So, yeah, I went out when you like, last class. So here's the chapter thing. Here's the first paragraph. All right. Let's go ahead and take a 2-minute break before we get in, make sure we understand how the lab's going to run.